The next several videos focus on a group of molecules that are extremely biologically important, referred to as carbohydrates. In this video, we are going to introduce the topic of carbohydrates before we dig in to later videos where we'll get into more details related to this essential group of biomolecules. When we use the term carbohydrate, let's first talk about what we are referring to. We can break this term down: carbo, referring to carbon-based; hydrate, referring to water. Much like in some of our prior segments, we referred to hydration reactions. Hydrate here is referring to the presence of water being within the molecule. So we can fill in the hydrate part of this as derived from water, and the carbo part of this name as referring to the molecules being carbon-based. In other words, they are certainly organic molecules. Carbohydrates are referred to as this name being derived from water and carbon-based because the first known members of this family of molecules had the formula CnH2O M, where N represented the number of carbon atoms, M represented the number of water units, where if we looked at the formula for the molecule, we could break it down into a certain number of carbon atoms and a certain number of water units. For example, the most well-known, arguably, sugar is glucose. Glucose, in its cyclic form, which we'll learn about later on, has the molecular formula C6H12O6. So if we were referring to that and matching it up with the template here of carbohydrates being CnH2OM, we would say that we have, of course, 6 carbon atoms. So N in that formula is equal to 6. Cn, there's 6 carbons here. And then with the water being represented as H2OM, we could fill that in to meet this template by reflecting this as 6 water units, because 6 water units times 2 hydrogens would make 12 hydrogens total. 6 times the oxygen atoms here would equal 6. So therefore, glucose fits this formula that is the prototypical formula of carbohydrates. Now keep in mind that as time has gone on, there are exceptions to this formula. This is just the prototypical formula, and this is the formula that led to why carbohydrates are referred to as carbohydrates, because of that water and carbon origin. But there are certainly lots and lots of exceptions now known to this formula. So don't completely rely on that when you're thinking about whether something fills the definition of a carbohydrate or not. In general, carbohydrates are going to, from a chemical perspective, be classified as polyhydroxyaldehydes. There's a lot to unpack there, so let's go ahead and write that down. Poly, meaning many. Hydroxy, referring to the OH groups, much like when we were talking about alcohol, same terminology here. An alcohol group, an OH group, is called a hydroxy group. And aldehydes we learned about in a very recent unit. So carbohydrates will have, in other words, multiple OH groups, along with an aldehyde functional group. Remember, an aldehyde is a carbonyl group directly bonded to a hydrogen, and then we can be connected off to whatever else we need over here where the squiggly line is. Additionally, carbohydrates also commonly are seen as polyhydroxy ketones. And that is yet another reason why we covered aldehydes and ketones in the same unit, was because both of these groups are found within carbohydrates. So in the polyhydroxy ketone, the ketone unit, recall, is a carbonyl group that has carbons on each side of it, and whatever's connected off to here is the squiggly line. Can be a variety of functional groups, but it has to have a ketone in it. So in the case of carbohydrates, what we're going to see as the hallmark feature is that they have an aldehyde group or a ketone group, and the molecule also has lots and lots of hydroxy groups, meaning poly, meaning many. One way that we can recognize carbohydrate molecules from the names that are provided for these is carbohydrate names will have the OSE suffix. So if you are looking and quickly glancing through a list of names and you're trying to determine whether a particular molecule is a carbohydrate or not, the names of carbohydrates will have OSE as the suffix for the name, such as glucose, sucrose, fructose, cellulose, ribose. A wide variety of other possibilities come into play there. But if you see a compound that has the OSE suffix, you can be sure it is a carbohydrate. Now, there are some carbohydrates, such as starch, that do not use the OSE suffix. But if you see something with an OSE suffix, rest assured that molecule is a carbohydrate. Let's take a look at some example carbohydrates. We will get into these, including their chemical structures, in more detail in later videos. For now, we're focusing on an introduction to these molecules, why they're important and where we find them. And for that, we'll rely on some examples. Carbohydrates play a huge number of vital roles in organisms ranging from humans to fungi to bacteria to plants, very universally across life. Carbohydrates are very notable as a source of energy. So one key function of carbohydrates is a source of energy. Carbohydrates play that role in a variety of different ways, using a variety of different carbohydrate molecules. Some specific examples of that are glucose, generally considered to be a very simple, easily metabolized sugar for fast energy in the human body. So I'll just describe glucose as fast energy. It is a simple sugar, as we will learn later on. It is comprised of just one sugar unit, and that is what makes it a simple sugar. In stark contrast to that, at the other end of the sugar spectrum, or the carbohydrate spectrum, we have glycogen. Glycogen is a complex carbohydrate. It is the body's main way of storing glucose, and what happens in glycogen is a multi-branched polysaccharide of glucose units. And I'm going to abbreviate glucose as GLU. And the purpose of glycogen is it's used to store glucose within the body. And the way that it does that is a bunch of glucose units linked together via chemical reactions. We will learn about those specific chemical reactions later in this unit. Once those glucose units have joined together to form a huge structure, we refer to that as a polysaccharide. A monosaccharide is the individual sugar unit. A polysaccharide is once a bunch of those units have joined together to form a complex structure. And that complex structure isn't just a linear chain of glucose units, but instead it has a bunch of branches. Much like when we talked previously about structures of molecules and IUPAC nomenclature, and we talked about branches coming off of parent chains. In the case of polysaccharides, that's a very extreme example of that, where the structure has many, many, many branches coming off of it. But all of those are repeating glucose units, and that represents a very valuable way to store glucose within the human body. If you've ever heard of an athlete doing something like glycogen loading by eating a lot of pasta before a big endurance event or something like that, they're trying to build up their glycogen reserves so that then during the event, the body can tap into those and break those down into glucose and metabolize the glucose to be a source of energy. The analogous molecule to glycogen in the plant kingdom is referred to as starch. So within humans, bacteria, and fungi, glycogen is king for storing glucose units. Within the plant kingdom, starch is the source of storage of glucose. So this is going to be our polysaccharide of glucose units within plants. In addition to being a major source of energy for fueling cells, carbohydrates also are well known for their role in playing structural support. A couple of examples of carbohydrates that are well known for their roles in structural support include cellulose which an example of an organism that is high in cellulose is the celery plant. And the reason why celery has its very distinct properties and is rather hard to chew is because cellulose provides the structural support of that plant. Chitin is another example of a structural support polysaccharide. Chitin is most notably in seashells and other crustaceans. And it gives the shell its very rigid structure. A third example of carbohydrates and the central roles they play in biology is carbohydrates are an essential component of genetic material. A prime example of that is one of the building blocks of genetic material is a compound called ribose, and the OSE suffix there is our telltale sign that this must represent a carbohydrate of some sort, because OSE refers to carbohydrates. We previously used the term saccharide a couple of times in this discussion. Now we're going to go into a bit more depth on that topic. The term saccharide comes from the term Latin saccharum, which means sweet. Carbohydrates are also known as saccharides because many noteworthy carbohydrates have a very sweet taste. Particularly, carbohydrates that have 5 to 12 carbon atoms are generally quite sweet. In contrast, more complex carbohydrates, such as glycogen and starch, that have many more carbon atoms than just 12, are generally not sweet, but 5 to 12 carbon carbohydrates, and some that are even a bit more complex than that, are generally sweet in taste. And that's why they are referred to as saccharides. And in fact, the first examples of carbohydrates were all sweet, and that was why the term saccharide stuck. And then later on, as science advanced, additional more complex carbohydrates that did not have that sweet taste were discovered, but were still structurally similar and represented complex molecules built from carbohydrates, monomer building blocks, and were thus stuck with the name saccharide as well. A monosaccharide, mono meaning one, sugar meaning saccharide, refers to a compound that has one simple sugar group. So a monosaccharide is a molecule with just one simple sugar group. Most monosaccharides have between 3 and 9 carbon atoms, with 9 being at the extreme end, 3 being at the very short end, somewhere between 5 and 6 carbons being quite common. The general formula for an acyclic monosaccharide, meaning a monosaccharide that is not a ring but instead is a chain of atoms, is CnH2nOn. So I'm going to plug that in here as the general acyclic formula. A meaning without, cyclic meaning acyclic meaning without a ring. So the general acyclic formula is CnH2nOn. And you would find that glucose with the formula C6H12O6 fits that formula perfectly, as do the majority of monosaccharides that are common, which we will encounter. These acyclic monosaccharides have one aldehyde or ketone group. And I'm going to add the addendum here that we're still referring to specifically acyclic monosaccharides. When we get into a later video, we are going to find that through chemical reactions, these monosaccharides can exist in both acyclic linear forms as well as in cyclic forms. And once they form the ring structure, the aldehyde or ketone group no longer exists because it is destroyed within the chemical reaction. So that's why I add the addendum here that when we say that they have an aldehyde or ketone group, we're referring specifically to the acyclic form of the monosaccharide. An example of a monosaccharide, the simplest monosaccharide example, would be glyceraldehyde. Let's draw out the structure of glyceraldehyde here. Glyceraldehyde begins at the top of the molecule in a Fischer projection with an aldehyde group abbreviated CHO. Then next in the chain is a CHOH group. Like so. And then finally, at the end of the chain is CH2OH. And as we learned when we were drawing Fischer projections previously, in the last video, we represent the chiral carbons here as these intersections of these crossings. So there is a carbon atom right there. That carbon is a chiral center because it's got 4 different groups bonded to it. And this carbon, hence, could adopt 2 different configurations, R and S, or alternatively, you could refer to that as D and L. And indeed, typically, sugar molecules go by the D and L configurations, such as L-glucose versus D-glucose, representing different stereoisomers. So what we will do in following videos is we will look more at the stereochemistry of these molecules as one key topic that we refer to. Now that we have a general introduction to sugars, including some of the key terminology such as saccharide, such as looking at these molecules as polyhydroxyaldehydes and polyhydroxy ketones, and thinking about some common examples of general types of carbohydrates such as glycogen, starch, cellulose, ribose, and others, we can now get into the topic in more depth in the upcoming units. Stay tuned for that.